All right, the question I had was, how do you determine the number of valence electrons? The number of valence electrons, the easiest way is just to look. For main group, which is the S block and the P block here, the number of valence electrons is given by this number here. This is group 1A. Oh, this is a typo here, it's not 11. It should just be 1A right there. This is 2A. 3A, 4A, 5A, 6A, 7A, 8A. And that's the number of valence electrons. And so you just look. Antimony, how many valence electrons? 5. Carbon, 4. Silicon, 4. Fluorine, 7. And so that's the easiest way to do it. Now for the transition metals, it's a bit more tricky how you do it. Technically, in the transition metals, it's just the S that are the valence here. You know, so it goes 4S, 3D. The 4S are the outer metals. So usually 2. Here it would go 5S, 4D, 6S, 5D. So just the S. And the P are on the other side here. But the transition metals, don't worry about those. Just the main group. And so when we do our Lewis structures, we just count them off the periodic table. Yeah. For the test, you'll always have a periodic table. Next. That's just going to be next Thursday. Any other questions? We're going to finish up chapter 13. Chapter 13 today, and then start chapter 14. So, chapter 13, the next section, we're going to deal with this polarity of molecules. Well, we have polar bonds. Polar bonds are caused by, differences in electronegativity. We have differences in electronegativity that's going to polarize the electron cloud one way or the other. Well, we can have polar molecules as well. And polar molecules, why do we care? We care about polarity for things like physical properties, like water. Water is a very polar molecule. Oil is a nonpolar molecule. And so water and oil don't mix. And so this is not very good, I think, this slide. So I wouldn't worry too much. In fact, let's just go straight to the examples here. Methane. Methane looks like this. What does this look like to you? Tetrahedral, good. Yeah, very familiar shape, tetrahedral shape. And so methane looks like this. You guys saw the tetrahedral in the models lab, right? The other day. And so this molecule, typically what we do is we put 2 in the plane like this, and then 1 comes out, we show as a wedge, and then 1 goes in, which we show as a dash. So this is the molecule here. Well, methane is what we call a hydrocarbon, and hydrocarbons are compounds of just hydrogen and carbon. We look at the electronegativity difference between carbon and hydrogen. Carbon's at 2.6, hydrogen is at 2.2. The electronegativity difference is 0.4. Is 0.4 significant or insignificant? Insignificant. And so what we say is that the polarization of the electron cloud is minimal. It's pretty symmetric. That is, it's pretty even tug of war for electron density between the two. Just a slight polarization towards carbon, because carbon's just a slight bit stronger. Otherwise, for the most part, these bonds are nonpolar. And so it doesn't matter. As long as it's a hydrocarbon, a compound of carbon and hydrogen, the bonds are nonpolar. If the bonds are nonpolar, then the molecule will be nonpolar as well. And so that would be like oil, you know, oil, nonpolar, water, polar. And so we could look at some other hydrocarbons. Let's take a look. You look at this one looks a bit more complex, right? Even though it looks a bit more complex, it's a compound that consists only of carbon and hydrogen. Therefore, it's easy. It's got to be polar or nonpolar? Nonpolar. Nonpolar. Pretty soon people get tired of writing out all the atoms, especially organic. If you get into organic chemistry, you get large complex molecules like this, and if you're writing out all the atoms, it becomes a lot of work. And so what they do is they just don't show the atoms, they just show the bonds. Here they're showing carbon here, like this CH3 here, a C with 3 hydrogens on it. And this is going to bond to carbon, so imagine this is carbon here. And then we have another carbon. So what we're going to see is we're going to see this kind of zigzag arrangement of carbons. So the carbon here, carbon there. Now if we got a carbon here, so let's say this is a carbon and another carbon here, that means we're going to have 2 hydrogens. They aren't showing the hydrogens on here. There's 1 hydrogen sticking out, 1 hydrogen sticking in. And then we repeat this zigzag pattern all the way across. Do you remember seeing something like this? The models lab, yeah. And so this is the shorthand way of drawing more complex structures, like that. Here. But is that molecule polar or nonpolar? That molecule is nonpolar. Nonpolar. We're going to come back to this molecule in a second. How about this molecule? This one's polar or nonpolar? It's nonpolar. All hydrocarbons are nonpolar, so that's pretty easy. And so all hydrocarbons are oil-like in their interaction with water. They just don't like water. And so let's take a look at this hydrocarbon and let's talk about the naming of this. If you look, what are they doing with these blue numbers? What they're doing with these blue numbers that you see here is they're trying to find the longest chain, longest continuous chain of carbon atoms. And so it doesn't matter how they go left to right, you know, top down, bottom up, you know, zigzag. It doesn't matter how you go. You're just looking for the longest continuous chain, and they found it. The longest continuous chain will be 6 carbons. 6 carbons gets the hex prefix. Now the ane, this ane part means that they're all single bonds, carbon-carbon single bonds. If we have an ene, there's a double bond. If we have an ine, which is YNE, there's a triple bond. Well, there are only single bonds here. And so it's a hexane. But there's things that are attached to this hexane. You see this? Let's take a look at the name. It's 2,2,4-trimethyl. Tri being 3. And so there are 3 methyls. What is a methyl? Meth is for how many carbons? 1 carbon. And so here, if we look on carbon number 2, we have a methyl. This is a methyl, CH3, methyl. Methyl comes from, free radicals. Like the methyl radical. The methyl radical would look like this. It'd be CH3 with 1 dot there. Dot. And so you'd know, is that stable or unstable? That's unstable. This is what we call a dangling bond or free radical. And what does it want to do? It wants to bond to something. Well, here it is. It just bonded to carbon number 2. So we got a methyl that's bonded to carbon number 2, another methyl, and so we got 2 of them. So we call it 2,2. That would be di. And then if we go to carbon number 4, do you see another methyl here? Yeah, there's another methyl. So this is a 2,2,4 hyphen trimethyl hexane. But yeah, it's a complex molecule. But it's going to be nonpolar. How about this molecule? What's the longest chain that you see here? The longest chain is 13 carbons. 13 carbons is what? You probably, yeah, it's not one that you have to memorize, but can you see what it is? What are they calling it? They're calling it tridecane. Tridecane. So 1, 2, 13 carbons. And then look at what's on carbon number 3. On carbon number 3, although it's not written here, there's a carbon at that kink. And so that's a 1 carbon, 2 carbon. There's a 2 carbon thing on carbon number 3. 2 carbons gets what prefix? F. So look at carbon number 3, there's an ethyl group here. That kind of. How about carbon number 5? Do you recognize that? CH3 is a. Well, this is CH3CH2. Well, then you don't see the hydrogens because they eliminate the hydrogens. But this is CH3, which is a. What kind of group? Methyl group. There it is, methyl group. It looks like there's more of them here. So that's carbon number 5. There should be another one on carbon number 9. Do you see it? Here, and one more on carbon number 11. So that's 3 methyls or trimethyl. Here. The carbon 3. Carbon 7 has 2 interesting groups here. Do you see carbon 7? What are these groups called? Well, those groups are a lot more complicated. They're just bigger, so we're going to skip that.
So all these are connected to carbon?
No, to the carbon chain. We're looking at the carbon chain. The carbon chain is called the parent, and then we see and what's attached to the parent. Sometimes we have a choice, you know, about the numbering here. Let's take a look back here. If we go back to this one, take a look at how they numbered this. You know, could we have numbered it, well, we want the longest chain, but what if we numbered it this way? Rather than calling this carbon number 6, let's call this carbon number 1. So if we call this 1, 2, 3, 4, 5, 6, then we get a little different name. If we did it that way, we'd have a methyl on carbon 3 and a methyl, 2 of them on carbon number 5, if we reverse the numbering. And so what would have resulted would have been 3, 5, 5 trimethyl. So 3, 5, 5 or 2, 2, 4. Which one's better? Well, both of them are the exact same thing. Both of them are exact same molecule, so we have to pick one. So which one should we pick? We're going to pick the one with the lower numbers. And so 224 is better than 355. We want a lower numbering system. If there's a choice. If there's no choice, then we only have one numbering system. Okay, those are some hydrocarbons. Okay, so in methane, the bonds are nonpolar, so it's going to be nonpolar. However, in something like this, CCl4, how would you name CCl4? Carbon tetrachloride. In carbon tetrachloride, the bonds are polar. It's hard to tell because they drew the deltas the same size over there, but these deltas are much more bigger than those deltas over there. And so the bonding is much more polar. Do you guys know how to draw a tetrahedral on the board or on paper? No, we'd have a carbon here, and then how do I draw the others? Well, I'm gonna draw like that. One bond to chlorine in the plane like this. And then one bond to chlorine in the plane like this. And so I put two in the plane, and that means one sticks out and the other sticks in. So this is what I'm trying to draw on paper, is I'm just gonna try to orient this in the plane, and that means that one sticks out here, one sticks in here. So that's my tetrahedral arrangement. Well, which one's more electronegative, chlorine or carbon? Which one's more electronegative? Chlorine. And so the electron cloud is going to be distorted. The electron cloud is going to be polarized towards chlorine. That is, chlorine has a stronger pull. So results in something like that. When the electron cloud is distributed asymmetrically like this, then one end gets more negative charge, the other gets more positive charge. And so we have set up a delta minus and a delta plus. You know what we call this? We call this a bond dipole. It has a positive end and a negative end, two poles, dipole. There's another way of representing this. The other way of representing it is by using an arrow. The arrow points towards the more negative end, and the tail is shown with a little positive sign there. And so this shows that it's more negative here, more positive there. So we definitely have a polar bond there. How polar is it? Do you expect it to be ionic, polar covalent, or just non-polar covalent? Where do you expect a carbon-chlorine bond to fall? Polar covalent. You know, if it were metal and a non-metal, then yeah, maybe ionic. But this is two metals, non-metals. All right, now we got polar bonds. Unlike methane, you know, and unlike all the other hydrocarbons, we have a polar bond. So if we have a polar bond, is this water-like or oil-like? You know, non-polar species are oil-like, polar species are water-like. So is this more water-like or oil-like? Water-like? Well, it's not just the polar bond. If it was just this polar bond, I'd say yes, it's water-like. However, what we have to do is we have to do something called vector addition. And that is, what we have to do is we have to add up all the bond dipoles in 3 dimensions. In other words, we have a bond dipole that points towards this chlorine, a bond dipole that points towards this chlorine, and a bond dipole that points towards that chlorine. And so you have to imagine that the carbon atom here is being pulled towards all the chlorines. But when you look at this tetrahedral, one thing to notice about the tetrahedral geometry is the symmetry. If you look at the symmetry of this, it's what we call spherical symmetry. For example, no matter which of these I grab, you know, it always looks exactly the same. And so what we say is these 4 are equivalent. And so another way of thinking about this is if you put this inside a sphere, then it's perfectly balanced in the sense that you only have these 4 points of contact here. And so if I had a tug of war, let's say these 2 are pulling down. These 2 are pulling down, but what's happening with these 2? These 2 are pulling up, equal and opposite. And so what happens in 3 dimensions is this. If I were to sum up the bond dipole, the sum of the bond dipoles in 3D over 3 dimensions is equal to the molecular dipole. And it turns out the sum of these bond dipoles is going to equal 0 because there's going to be no net. You know, they're kind of cancel each other out. There's no net molecular dipole. And so, you know what? Carbon tetrachloride is oil-like. And so this carbon tetrachloride and water don't mix. But unlike oil, carbon tetrachloride is dense, so it sinks. Whereas oil is typically less dense, so it floats. So carbon tetrachloride and oil don't mix. Now let's take a look at this next molecule. How about this one? Do you know the name of this? Or how to name this? Actually, you don't. The rules that we had are naming binary molecular compounds. They aren't for naming, trinary or quaternary or whatever. So we don't know the rules for naming this. But I'll tell you the name of it. This is called trichloromethane or chloroform. If we look at this one, though, do the bond dipoles cancel each other out? In the tetrahedral here, they do cancel each other out, but in this case, they don't necessarily cancel each other out, because if I put, let's say I put 3 chlorines on the bottom and a hydrogen on the top, the hydrogen has no pull. The 3 chlorines are going to pull. So if the 3 chlorines are pulling towards each other, the net effect is it's pulling it down. Does that make sense? And so here, what we're going to do is we're going to take this arrangement and then just tilt it on its side. So we have the 3 chlorines out here that's going to be pulling straight out this way. And so that's the molecular dipole, the net dipole they call it. The net dipole is the sum of the individual dipoles, and these 3 are just pulling out. It's going to pull out that way. I didn't have enough greens here, but this next one I can do. The next one is dichloromethane. So let's take a look at that. All right, when we look at dichloromethane, it's oriented like this. So these are in the plane, these 3 atoms. That means this hydrogen sticks out and this hydrogen sticks in. So this would be a wedge, this would be a dash coming in. Now, the carbon hydrogens are nonpolar, but this is polar. So what's more electronegative? Chlorine. So it's pulling the electron cloud out here and out here. So net, if both of these are pulling, the net dipole is going to be coming straight out like this. And so this would be polar. So this would be more water-like, right? How about this one? Is this one polar or non-polar? Well, that's a little easier. That last one there in this series, be like this, chloromethane. If we look at this one here, these aren't pulling, but this one's pulling here, so it's just pulling up. So it turns out that the bond dipole is the same as the molecular dipole in this case. So this would be a polar molecule. So we look at how about CO2? CO2 is a non-polar molecule. CO2 and water don't mix, so CO2 just bubbles out of water, right? And so CO2 is nonpolar because the bonds are nonpolar? Are the bonds nonpolar or polar in CO2? The bonds are polar. The reason why CO2 is nonpolar is because the net is 0. One's pulling to the right, the other's pulling to the left. They're equal and opposite, so they cancel each other out. There's no net dipole. Even though they're polar bonds, it's a nonpolar molecule. Whereas H2O has a different shape. You know, H2O is bent like this. Since H2O is bent like this, yeah, it's polar. We got a polar bond here and a polar bond here. They don't cancel each other out. And so if one's pulling this way, one's pulling this way, the net movement is up. And so the net dipole is going to be up here. What's that? And so water is very water-like. Water likes water. All right, any questions on this here? molecule polarity. All right, we're going to talk about organic chemistry next. Well, actually, we've been talking a little bit about organic chemistry. Organic chemistry is carbon compounds here. Chemistry is focus on carbon compounds. Not all carbon compounds are organic, though, but they're a large number. And it's kind of weird because if you look at all the compounds that are known, and there are a lot of elements in the periodic table, but most of the compounds that are known are carbon-based compounds. I mean, if you look at it, there are millions upon millions of carbon-based organic molecules, and there are just hundreds of thousands of everything else. You know, so if you take the entire rest of the periodic table, you know, how much variety do you see? How much variety do you see in oxygen-containing or oxygen-based? Not much. You know, oxides, chlorine-based, etc. No, the reason why we see so many carbon compounds is carbon doesn't mind forming long chains. You know, 4 atom, 2 atom, 13 atom, 22 atom. You can form these long zigzag chains of carbon atoms. And that doesn't apply to a lot of other molecules. A lot of other molecules, or not molecules, but atoms don't necessarily like to do that. So this is what they're saying. Carbon atom, right size and right strength of bond formation helps form stable molecules, but weak enough to undergo reaction as well. All right. It's the rich bonding environment of carbon. Inorganic chemistry is the chemistry of everything else, basically. Everything else in the periodic table is considered inorganic chemistry. There are some carbon-containing compounds and ions that aren't necessarily organic, like carbonates are considered inorganic, cyanides, inorganic, oxides of carbon, carbon monoxide, carbon dioxide, inorganic, and a few others. Everything else is organic. We talked about hydrocarbons, so we'll talk about the alkanes first. The alkanes are all single bonds. It's just a compound of carbon and hydrogen. If we have an alkene, there's a double bond, and alkyne, there's a triple bond. But all we're going to look at are the alkanes. So let's take a look at some alkanes here. What's the longest chain of carbon atoms here? You see the zigzag? The zigzag's a result of the what is the structure of this carbon here? The geometry? Tetrahedral. And so the zigzag's a result of the tetrahedral. You got two in the plane. And so they're going off the top. The top one's in the plane, this one's in the plane. That means one sticks out, one sticks in. This one's attached to another carbon. Do you see the other carbon? We draw 2 in the plane, one coming out, one going in. And so the other carbon's like this. 2 in the plane, one coming out, one going in. And then we attach it to this carbon, and then we have this zigzag. Do you see the zigzag pattern? Pretty much is very common. What's the longest chain of carbon atoms? Four. Does everybody see that? 4 carbon atoms? No. Just the black ones. 1, 2, 3, 4, which means bute. Are there any double bonds or triple bonds? No, that's all single bonds. So ane, butane. This is butane. But there are different butanes, you know, for carbon atom hydrocarbons, and so this is called normal butane and butane. Just a straight chain. This one's called isobutane, because again we have 4 carbons, but do you see the structure is a little different? Both of these are C4H10. So both of these have the exact same molecular formula, but they have different structures. They also have different structural formulas if you write it differently. But even though they're both C4H10, their properties are gonna be different, and those are called,
What's the longest chain ever? Is there a limit to how long the chain can go?
oh, it's chain, there's no limit. Depends on how much you can synthesize. There are things called polymers, you know, and the chains can be extremely long, thousands of carbons.
The scientists that are trying to like make the longest chain ever.
I'm sure.
Guinness World Record.
I'm sure there must be something. Yeah, people are trying to do the biggest ring on the other things, but let's see the longest chain of carbon atoms.
That sounds interesting.
I don't know, that's interesting.
Yeah, some coefficient.
This is just practice of finding the longest chain. For 11. Oh, this is longest chain of linear. Take a look at that. Completely straight line. Linear carbon atoms, 6,000.
That's the number to beat.
But that's linear. The longest chain of atoms that they don't have to be linear. Sometimes it's very tricky. You know, this is why there's so many websites of finding the longest chain. I don't want us to do this one. So. How many carbon atoms do you see as the longest chain? Okay, what did you get? 7 is not correct. Try again. 9. 9 is correct. Do you see that? 9 is the longest chain, so there's no name. You know, there would be no double bonds here. So no name is the then we have different substituents on there. If I look at the shape, I can tell you what the names of the substituents are. For example, this one on the left here is an ethyl. This one here is a methyl. This one up top this one's called an isopropyl. Isopropyl because it has like a fishtail on there. A couple more methyls. Do you guys see that? Maybe, maybe not. Actually, what were we looking for? The world's longest chain of carbon atoms. Longest chain of carbon atoms ever measured. This is just a whole bunch of sites to help you find, because sometimes it's hard to see the longest chain of carbon atoms. It's going to take more time to find it, though. It's got to be more than 6,000 because that was just the. It's got to be way more than 6,000. Sure. And we'll just continue on. Well, anyway, these are two things are called isomers. This is called isobutane. What was iso again? Iso is just kind of this fishtail deal here. This is the fishtail deal. Isobutane. So it has 4 carbons. Both of these have the same molecular formula, C4H10, but different structures. Those are called same molecular formula, different structures are called isomers. Except they have C4H10, but these are called structural formulas. They have different structural formulas because structural formulas try to show the skeleton, how it's bonded together. It's isobutane. There's another name for isobutane. Can you tell me the other name for isobutane? Can you tell me what the longest chain of carbon atoms in isobutane is? Is it 4? You would think it's 4. I would think it's 4, but it's not 4. What is the longest chain of carbon atom? 3. If it's 3, we don't call it but. What do we call 3? Pro. And so what's another name for this? We don't use iso in this case. We would just call it. We'd call it. Well, we'd number it. How would we number? Maybe what's the chain? This chain? 1, 2, 3. On carbon number 2, what is there? A methyl. So this would be called 2-methyl propane. But you can only have a methyl on carbon 2 because if you put a methyl on carbon 1, it'd just be butane. So we just call this methyl propane. Methyl propane. Let's look at pentane. Pentane has how many carbons? 5. So this is called normal pentane. Normal pentane is just a straight line chain. Chain. 5. This is isopentane. Isopentane has this little fish tail on the end. Do you see that? Isopentane. This is called neopentane. Neopentane has this tetrahedral type shape, like spherical type shape to it. And so we have N-pentane, then isopentane. And isopentane has another name. What's the longest chain? 4. And so what would another name for isopentane be? In fact, this would be a more systematic name. What would it be? Methylbutane. But if we just left it at methylbutane, well, there could arise situations where it's a little bit confused if there are more substituents here. So for example, here, how would we name this? If we name this carbon 1, carbon 2, this would be 2-methylbutane. Or if we go backwards, let's name this 1, 2, 3, 3-methylbutane. So is this 2-methylbutane or 3-methylbutane, depending on if we count left to right or right to left? Which one is it? It's going to be 2-methylbutane, a smaller number. How would you name this one? What's the longest carbon chain? 3, which would be propane. And then we have, on carbon 2, we have 2 methyl groups. So this would be 2,2-dimethyl propane. But actually, you don't have much choice where you put the methyls because you can't put it at the end. That would increase the chain. So this would just be dimethyl propane. Based on substituents can come in a variety of shapes, sizes, and other things. So for example, this is the methyl radical. Do you know what the hydroxyl radical looks like? The hydroxyl radical looks like this. That's the hydroxyl radical. And so this would be the hydroxyl group here. Hydroxyl groups are found in alcohols, you know, and alcohols are going to have this like take a look at the simplest alcohol. The simplest alcohol is going to be 1 carbon alcohol. And let's try to draw that with a wedge dash diagram. So it's going to be like this. And then like that. So I start my zigzag here. You know, everything's in a plane. Like this. Sure. This is called methanol. Methanol also goes by the name methyl alcohol. You know, this would be the methyl group, CH3. This is alcohol, methyl alcohol. Look like this. So if we look at this first carbon here, the first carbon, the CH3, is what shape? Tetrahedral. The HCH bond angle should be about 109. The HCO bond angle should be about 100, and the HCO angle should be about, no, because we just said that this is tetrahedral. In tetrahedral, all the angles are 109, no matter where you look at it. It's got this spherical symmetry. Everything's the same. And so the HCO angle is also 109. They're all single bonds, so we don't expect much distortion. All right, now this is going down to oxygen. The oxygen, what is that? Tell me about the geometry around oxygen. Bent is correct for its molecular geometry. What is its electron geometry? The set geometry, the electron pair geometry, or the electron group geometry? Tetrahedral, yeah. And so this is tetrahedral, like this, where what we have is we have the hydrogen up here, and then we have one lone pair coming out, one lone pair going in. But the carbon, oxygen, hydrogen, we're going to put flat in the plane. Have something like that. This would be methanol. Methanol, well, is that a strong base? Methanol, strong base? Hydroxyl and hydroxide look similar, don't they? OH. OH. So you might expect methanol to be a strong base like sodium hydroxide. Sodium hydroxide is a strong base because they both have OH. You know, although when I look at sodium hydroxide and I want to draw the structure, I draw something more like this. What's different about these two? What's different about these two is that water comes along. You know, sodium hydroxide is soluble. It's also something we call a strong electrolyte. So if water comes along, it breaks apart the ion to form an electrolytic solution, a solution of ions. And so strong electrolytes break apart pretty much completely. However, if water comes along here, is it going to break apart the hydroxide from the... Will it break off the... No, because the bond is different. This is a polar covalent bond. This is an ionic bond. The bonding is different. So they're going to behave totally different. In fact, methanol is not even considered acidic, or basic. Not really considered either of them. That's methanol. All alcohols are going to have this group here, the COH. It's an alcohol. Alcohols are not strong bases. What's an ether? An ether is very similar to an alcohol. The only difference is we're looking for this instead, a COC. This would be an ether. This oxygen's tetrahedral electron geometry, bent molecular geometry. So this would be an example of ether here. So I'll make this zigzag. So I'll put this hydrogen in the plane. So this hydrogen in the plane, carbon, oxygen, carbon, and then I'll put this hydrogen in the plane. So if I have two in the plane, then one's coming out, one's going in. So two in the plane, one comes out, one goes in. You know what this is called? What that ether is called? Okay, do you know what this is called? This CH3 is called, this drawing doesn't look so great. CH3 is called methyl. How many methyls do we have? It's dimethyl. And so the name of this is called dimethyl ether. Dimethyl ether. Take a look at the structure of dimethyl ether here. Dimethyl ether. This is one of the most common ethers. Does this look like a good structure to you? I mean, I guess it shows kind of the. It's not very three-dimensional, is it? Maybe this is a little bit better. There's a methyl group here. There's a methyl group here. They did the zigzag. You know, I have mine flipped the other way. So here they do. That's one thing we commonly do is tetrahedral. Do that zigzag, zigzag. So we get two in the plane. One comes out as a wedge. The other goes in. Over here is a tetrahedral too. Two in the plane. One comes out, one goes in. This is tetrahedral electron geometry. And so two in the plane, which is these two bonds. One lone pair sticks out and up. Another lone pair sticks in and up off the top. Okay, so here we looked at methanol. Methanol is kind of interesting because one end of it's kind of like water-like, you know, OH, water-like. The other end of this is oil-like, like hydrocarbon. So this is what they're calling the alkane portion, the hydrocarbon portion, and the hydroxyl or the water-like portion over here. Over here, do you know what this is called? Well, how many carbons do we have? We have 4 carbons. 4 is bute. Are there any double bonds? Ane. Is it an alcohol? Yes. COH is an alcohol. So butanol. Butanol. That's what we call that. Which one likes water more? Methanol or butanol? Which of those two do you think likes water more? Methanol? Methanol is correct, yeah. Methanol likes water more. In fact, methanol is what we call miscible in water. What miscible means is it mixes in all proportion. Does water like water? Yeah, water likes water. If you were to mix water and water, is there any limit to how much water you can mix with water? No, that's miscible. Methanol's like that. Is there any limit to how much methanol you can mix with water? No limit. Methanol and water, they love each other. They're going to mix in all proportions. However, butanol and water, they don't mix. butanol is pretty insoluble in water, or not very. It has very limited solubility in water. Why do you think?
Is it because the greater portion of the oil?
Yeah, exactly. It's the greater portion. This is starting to look a lot more oil-like than water-like. In fact, butanol, what about pentanol? How would pentanol be different? Pentanol would have one more zag here, right? Pentanol would have 5 carbons, which would make it more soluble or even less soluble in water. Even less soluble. So pentanol is not soluble in water. It's too oil-like to do it. Do you recall this was dimethyl ether, but this is not dimethyl ether. Do you know what this is? Diethyl ether. It has 2 ethyl groups, one here and one here. Ethyl groups are CH3, CH2, and hydrocarbons, 2 carbon hydrocarbons. So diethyl ether. Diethyl ether is I think it's still used in the illegal drug trade because diethyl ether is a good solvent. You know, it's kind of oil-like and water-like, right? And so diethyl ether is used, I guess, for purification or something like that. And what they do is what happens is that diethyl ether is very volatile, means it evaporates easily. But as it volatilizes, the vapor is very heavy and sinks to the floor. And so if you have some ether on the counter, what happens is the vapor, it doesn't rise to the ceiling. The vapor goes onto the table and then goes on the floor. And this stuff is electron rich. You know, the methyl group, these are called methylene groups. These carbons are electron rich. And so it's highly flammable. And so the fires burn from the floor up. And so even chemists, who aren't involved in the drug trade are very scared of ether fires because of the potential for being completely engulfed in flames. And so, anyway, let's look at this one. This one, what's this called? Methyl. You know what this one's called? Well, it's cyclo. Cyclo is good. It's a cyclo 6 carbon, so cyclohex. And then it's got some double bonds, so cyclohexene. But this one's special. When we have alternating double, single, this is called aromatic, and it has special properties. This ring is called benzene ring or phenyl ring as a substituent. So this would be methyl phenyl ether. Methyl phenyl ether. How about this? What if I knock one of these ethyls off and replace it with a methyl? So let's say I had an ethyl methyl. If it was an ethyl methyl, would I call it ethyl methyl ether or would I call it methyl ethyl ether? Which would it be? Methyl ethyl ether or ethyl methyl ether? Ethyl methyl. Ethyl methyl because it sounds better? No. It's because it's alphabetical. And so here, methyl phenyl ether. Now, let's take a look at the geometries around here. What is this? This carbon is tetrahedral, 109 angle. This carbon is tetrahedral. They drew it funny, though. We should have the zigzag pattern, but what they did was they tilted it. And so it screwed up the whole thing. There should be 2 in the plane, but there's none in the plane here because the way they're showing this is like this. There are none in the plane because they're showing 2 sticking out like this, and then 2 sticking in like this. Usually we tilt it so that we get 3 in the plane, 1 coming out, 1 going in. But what they did was they tilted it like that. Oh, why? This is tetrahedral. What is this? Bent at what angle? Yeah. We have 2 bents. There's a bent at 109 and bent at 120. This is bent at 109. How do I know? Because there are 2 lone pairs there that aren't shown. And I want you to show the lone pairs, like this. They aren't showing the 2 lone pairs. Normally what we do is we draw the bonds in the plane, like this. And so that means 1 lone pair is sticking out, 1 lone pair is sticking in. Drawn like that. Let's go over here. This is tetrahedral. This is bent at 109. What is this? Just this 1 carbon. What would you say the geometry around that 1 carbon is? Not tetrahedral. Trigonal planar. This is trigonal. In fact, all of these are trigonal planar. And so this benzene ring or phenyl ring is completely flat. Interesting. So there's no wedges, no dashes, because everything's flat in the plane. There are a lot of substituents out there. And so it's just learning some of the names of these substituents. So let's take a look at some of these substituents here that we might encounter sometime. So we already encountered the methyl, the methyl substituent. If we have 2 methyls, it's di, 3 methyls, it's tri, 4 methyls, it's tetra. This one's the ethyl, CH2, CH3. This one's not really a substituent. This is the hydroxyl or hydroxy. This is the oxo or carbonyl. This is the carboxy or carboxyl. This is the amine or amino. This is the F, which is fluoro. This is Cl, which is chloro. Br, which is bromo. And so we have a number of, and there are a number of ways of naming things as well. So we have those. You don't have to memorize it. The last one is the carboxylic acids. The carboxylic acids have the carboxyl group, the COOH group. These are all weak acids. One of them is borderline strong, Actually, a couple of them are borderline strong carboxyl. Like trichloroacetic acid, pretty strong. But here, but it's still weak. Looking at this is the easy, the simplest, which is 1 carbon. 1 carbon is called methanoic acid. Methanoic acid, nobody ever calls it that. Everybody knows methanoic acid as formic acid. This one should be called what? If this is methanoic, this should be called ethanoic, but nobody ever calls it ethanoic. Everybody calls it acetic. And this one should be, yeah, and it is. Because, once you hit propanoic, then there are no more simple names for these. But these are this is 1 carbon, 2 carbon, 3 carbon carboxylic acid. This is the carboxyl group, the CO2H or COOH. This group, this structure you should know well. These are very common carboxylic acids. You should know that well. And when we look at this structure, what do we see? This carbon is what? Geometry. Trigonal planar, right? And so that means this carbon, this oxygen is flat on the plane. This oxygen is bent at 109. So that's what we have here, bent. This lone pair sticking out here, and lone pair sticking in. So 2 in the plane, 1 sticking out, 1 going in. That's the carboxyl group, carboxylic acids. That's the end of chapter 13. So we'll stop here, take a break, and then we'll continue.